Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to I'm going to go over a method called the moment distribution for statically indeterminate beams. So you can see this beam has like three bays and with like two fixed supports at the end and two rollers in the middle. So I don't know how to solve it unless I have a computer. So, but the method of the moment distribution is a method that was developed almost 100 years ago by Hardy Cross in 1930. And the way he suggested, and it was so clever, he was a genius. He said, no, I'm going to take these three parts, like every time I see uh, a support like that, I'm going to assume it's fixed support. So I'm going to break that into three fixed supports. The only time I don't have a fixed support is if at the two ends, if these or one of them or both of them say were rollers or pins, I would leave them as rollers or pins. But the middle ones will always be fixed. So maybe we'll take another example that at least one or both the end supports are not fixed. So I would leave them as they are. But the middle will always be fixed. So after I break that into three pieces, I calculate the relative stiffness. So I have three bays and each one of them is fixed on both supports, and each relative stiffness would be 4. So the K would be 4 EI over L. However, if one of them was fixed and the other was pin, and that happens only at the two ends, like either on the end here or the end there, one of them maybe, not in this example, maybe pin, in which case the relative stiffness would be 3 EI over L instead of 4. And then I will take that ratio between, we'll see when we go over this example, but the steps are like that. We get this, first of all, we use fixed supports for all the middle supports. I would calculate the relative stiffness. I would calculate the fixed end moments. If I have two fixed supports, I can calculate the moment on the right and the left, whether this is a concentrated load, whether it's in the middle or not in the middle, or I have distributed loads. And you have a table that shows you based on the loading, you can find the corresponding moment. Then I would use the ratio of the relative stiffness to distribute the moments. What do I mean by distributing the moments? Suppose I calculate the moment here is 20 and the moment here, say, is negative 40. That doesn't make sense because they should be zero. If one of them is positive, the other would be negative, equal to it in magnitude. But if there is a difference, I will have to balance the moment based on the relative stiffness, as I will show you in a second. Then we do something is called carryover. Like every moment I will carry over half of it from here to there, from here to there, but I don't develop or send any moment from the fixed end support. I don't go from this moment from this side to that side. I will show you what I mean in a second. But so let's start by writing down the relative stiffness. So I'm going to say, I think I need another piece of paper here. I can say KAB equals, notice all of them are fixed, so 4 EI over 8 KBC is 4 EI over 12. Notice these are, both of them are EI. You can just cancel the EI and say it's 1/2 4 over 8 to 4 over 12, which is 1/3. 1/2 to 1/3 is basically, if you take a common factor of 6, you get 3 to 2. So 3 and 2, meaning they add up to 5. So 3/5, which is 0.6, and 2/6. So 3 to 2 is 3/5, and this is 2/5, right? The ratio is 3 to 2 or 6 to 4, meaning 0.6 to 0.4. Now, I know BC, so how about KCD? It's 4 EI over 12. They are the same, so it's 50-50, 0.5, 0.5. And since here it's a fixed support, I can write 1 and 1. What does that mean? Let's wait and calculated fixed end moments. The fixed end moment, if I have a concentrated load in the middle, P, and this is L, the moment would be negative PL over 8 and PL over 8. Okay, P is 200 times 8 over 8, because the length is L is 8. So this is negative 200. I'm sorry, negative 200 and positive 200. So for this bay, the 200 times 8 over 8 is 200. So you get negative 200 and positive 200. How about the distributed load? The distributed load, you get the moment would be negative WL square over 12 and positive WL square over 12. So negative 15 times 12 over 12. So the 12 and 12 cancel, you get negative 180. So this is negative 180. I'm sorry, this is positive 180 and this is negative 180, and this is 0 and 0. Of course, there is no load. So that's basically what I have. And now let's see what will happen. I will have to do two things simultaneously. Here is what we are going to do. I will say distribution or distribute and carry over. All right, if I look at B, I see that these two loads or these two moments are not equal. When I add them, I get 20 kilonewton meter. They should be 0, right? There is no balance. So how do I take the balance? I say these 20, I will have to make the sum of these two negative 20, so that when I add the moments, I get 0. But how do I distribute them? Well, 60% is here and 40% of that is that. So I have a difference of 20. When I multiply it to 0.6, I get negative 12. So I'm going to write negative 12 and positive 12. Negative. Why did I say positive? Negative 12 and negative 8. I don't know what I was doing. I'm sorry. Negative 12 and negative 8. So now if you add those together, you get 200 minus 180 is 20, minus 12 is 8, minus 8 is 0. So now I have balance. I'm going to do the same thing here. The 180, 50, 50. So negative 90 and negative 90. As I said, the carryover, you will take half of that will go here. Half of that will go there, and half of that will go there. And finally, half of that will go here. Notice, if I have a fixed support at the end, I'm not going to make, I'm not going to carry over from those. Though it's like 100% would stay here, but the difference here are divided 60 and 40. The difference here is 50-50. Okay. Now I'm going to go again and say distribute, carry over. Let's see what would happen. Remember what we said? We said that these four are balanced. Remember? 20 minus 20 is 0. But now I have negative 45. The negative 45, 60% as a positive moment will go here and 40% will go there. Okay? 60% is 27. So I'm going to say, but it has to be positive. I say positive 27 and positive 18. Notice 45 times 0.6 is 27. 45 times 40, 40% is 18. And both of them are positive. So when I add them up, I get 0. I have a balance. Same thing for the negative 4. I make it positive 2 and positive 2. See how easy it is? Half of that will go here. Half of that will go here. Half of that will go here. And half of that will go here. Keep going until, you know, the difference is like decimals and you can stop and say that's enough. But I still have 13 and 9 and stuff that, you know, you can distribute, carry over. Okay. We said that these are balanced. And now I have only one. So negative 0.6 and negative 0.4. Now I have another balance. The sum is 0. The 9 will be negative 4.5 and negative 4.5. And again, this will go as negative 0.3. This will go as negative 0.2. This will go here as negative 225. And this will go here as negative 225. And probably I will stop either next step, or we can do it one more time. Distribute, carry over. Again, the 1 and the negative 1 are balanced, and the 9 and negative 9 are in balance. So I only have negative 2.25. I will take 60% of that. So again, 2.25 times 0.6 is 135 positive, times 4 over 6 is 0.9. They add up to 225, so I have a balance here. The negative 0.2 would be positive 0.1 and positive 0.1. Again, these are 0. I'm going to take half of that, 0.675, 0.45, 0.05, 0.05. Maybe one last iteration and we can stop, because really it's almost, it's accurate enough, right? If you have a bending moment, you know, close enough. Distribution, 0.05. 60% of that is negative 0.03 and negative 0.02. 45% is negative 0.225, negative 0.225. And finally, I'm going to take half of that, negative 0.015, negative 0.01, negative 0.1125, and negative 0.1125. And that's good enough. Now, we end up saying I have negative 200 minus 6 plus 13.5 minus 0.3 plus 0.675 minus 0.015 equals negative 192.14. Let's go to the second one. I have 200 minus 12 plus 27 minus 0.6 plus 135 minus 0.03 equals 215.72. Let's check the next one. I have negative 180 minus 8 minus 45 plus 18 plus 1 minus 0.4 minus 2 1/4 plus 0.9 plus 0.05 minus 0.02 minus 0.1125. Negative 215.83. And again, the only it's because we didn't distribute that. So really it's better to distribute that 60% is here. So let's do that. Let's say 0.1125 times 0.6, you get 0.0675. If I add it to this, the 215 plus that, it's really 215.79875. And when I go here, and get this one, I added everything until, so again, how do I multiply? No, let's wait. Let's multiply 0.1125 times 0.4 and then add that to what we had here. So you get negative 215.7875, exactly the same. They have to be negative 215.79. And again, I didn't distribute that. We can distribute it as 0.005 and 0.005. Let's see what do I get on the left-hand side of C. I start with 180 minus 90 minus 4 plus 2 plus 9 minus 4.5 minus 0.2 plus 0.1 plus 0.45 minus 0.225 minus 0.01 plus 0.005. I get 92.62. Now let's go here and say 0.5. Oh, I'm sorry. There's no 0.5. It's 0. So negative 90 plus 2 minus 4.5 plus 0.1 minus 0.225 plus 0.005. And I get exactly the same, negative 92.62. Finally, I have negative 45 plus 1 minus 2.25 plus 0.05 minus 0.1125. And in fact, we can also take 0.0025, which is negligible. So we can say negative 46.31. And basically, having known that, you have the loads and you have the moments, so I can find the reactions easily, right? Because I can have this part, this beam. I say the moment here is 215.79 and here it's negative 192.14, and I have this load. If I take the moment about here, I can get the reaction on the left-hand side, so the reaction at B on the left, subtract it from 200, get the reaction on the right. And then this is the middle part. I have the distributed load half and half. So I'm going to take the moment from C about B plus the moment at B. I can get the support reaction here and the support reaction there to add them up and get the support at B. And once I find all the support reactions, I can easily draw the shear force and the bending moment diagram. It's really very straightforward. I don't want to, waste time doing all of that. It's so easy. Once you find the reactions, you can plot the shear force and the bending moment diagram. I think I'm going to stop here. And then next time, I'm going to take another example where at least one of the two ends is not a fixed support. I'm going to make it a pin or a roller, in which case I'm not. When I get the ratio of the stiffness, the relative stiffness, I would use 3 EI over L instead of 4 EI over L. If one is fixed and the other is pin, then you get 3/4. And that is called the modified moment distribution method, because the actual, the original one used 4 EI over L, but then we had to make a carryover of the moment from both ends. And it's a lot of work. I mean, you will get the same result, but if you just use 3 instead of 4 EI over L, if one end is fixed and the other is pin, you see, you don't have to do carryover here or there. It's just from those. The carryover go from the inner supports. I hope this will explain to you how we find, distribution and carryover. And once you do a carryover, you can stop when, they are very decimal parts. It's 0.11. It's, very small. It's very like a good approximation. If you have any questions, again, as usual, please leave me a note and I will get back to you as soon as I can. Otherwise, I wish to see you soon. Have a nice day.